Welcome to you all. So, I'm sure many of you are familiar with this children's game called Mousetrap. And the object of the game is to slowly build up a mousetrap. But that's not the point here. The point here is this is a solution to a problem. This is for catching mice. Now, you might look at this and you say, is it an innovative mousetrap? Yeah, it's kind of innovative. It's kind of out there and crazy. Is it elegant? Well, that's in the eye of the beholder. So today, I'm going to talk through some process patterns which are all dealing with some problems, particularly distributed systems type problems. Now, some of you might think, yeah, I could solve that problem with a framework. I could use a Netflix framework or a Facebook framework, or there's a lot of frameworks out there you can use. And that's true, you can. But this is different. This is BPMN CamundaCon. So what I wanted to do was, how much can we use the engine to kind of fulfill some of these problems and solutions? And more importantly, by understanding these problems and their solutions, hopefully it will inform you these are the kinds of things you need to think about in your own architectures and solutions. And also, by understanding how we've implemented these particular implementations, you'll get a better understanding of some of the internals behind the engine. So sometimes we need a little idempotency. So everybody here will be familiar with the fallacies of distributed processing. You know, there's infinite resources and infinite memory. The network has zero latency. The network never fails. How many people have experienced a transient network failure? Just about everyone. So what do you do? Well, if you're in the browser or in an app, the easiest way is I just press the reset button, the browser spinny bar happens, and everything's taken care of, so it works really well. But what if I'm an e-commerce client and I'm making an API call to the engine and I'm starting a process to fulfill a request, an order? What happens if that client gets a transient failure? Okay? Again, the easiest way for that client to recover is to just do a resubmit. And if I still get a transient failure, keep resubmitting until I actually get positive acknowledgement that the engine has received my request to process that order. But what happens if that process is not idempotent? We'll get multiple instances happening and running. So what could that mean? Well, if it's a fulfillment process, we might end up shipping the goods twice. Now, maybe the customer will return them. But what if that process was a foreign currency transaction and it was delivering foreign currency cash? Would the customer be as motivated to return? This happens. I've seen it. So the other thing which can happen is, what if that process results in a charge on a customer's credit card or a customer account? So in today's experience and customer experience paradigm, we really don't want those things to happen. So the question is, how can I make my process instances, particularly starting them, idempotent? One answer with the engine, let's assume that the e-commerce client generates a unique key as a reference and it uses that as a business key. So we could turn on a unique constraint such that, okay, client submits, gets an error, client resubmits. Because there's now a duplicate key detected by an index in the database, the engine can throw an exception. And that exception can roll back all the way to the client. And yeah, that works. But it's not a very nice experience for the client. You know, and Bernd talks about this quite a bit and says, you know, contain the errors. So how can we design an idempotent process which is much better experience for clients? So let's have a look at that. So here's a very simple process. The idea is client submits an order, we validate the order and we accept the order. There's some detect duplicate code, which I'll go through in a minute. And if it's a valid order and it's not a duplicate, we go through and we complete the process. And that's a happy path. What I'd like to highlight here is this asynchronous checkpoint. So as far as the e-commerce client is concerned, I don't need to wait with a blocking wait until that process is fulfilled. I really just need you to acknowledge that you've got my process, I know it's going to happen, and you can have control back. So we use an asynchronous continuation after the validation, which is effectively now control gets handed back to the client gets positive acknowledgement, happy days. Behind the scenes, it doesn't matter that there's multiple orders detected in the duplicate. So if we do detect one, what we'll do is we'll just quietly reroute away to that process instance doesn't matter. So one of them will get through, one of them won't. So let's have a look at that, actually in practice. How did we detect a duplicate? Now, this is a generic piece of code. You can put it in any process, and it will kind of work. And the way it works is as follows. We use the history service, and we're relying on the client submitting a unique reference number, which is unique to them, which is used as the business key. So the first thing we do is we create a historic process instance query, and we're looking for instances of this particular process definition. And we can get the process definition key from the execution context. Next thing we're doing is we're looking for processes which started after a particular date. And I'm going to come back to that in a sec. Once we've got that, the next filter is I'm looking for processes with this business key. So it's this type after this date with this business key. And I run that query, and we sort them into ascending order because really what I'm after is the earliest one. And then what I can do is, in my current process instance, I compare its ID to the earliest one I can find with this query. Now, if they're the same, then it's, well, you're the very first instance we've seen of this, so you're good, you keep going. But if they're not the same, then you're a duplicate, and you've come after the one which was gated through. So now what we can do is we can throw a BPMN error, and that will route the process to that unhappy path, which effectively just silently makes that process go away. Now, the question is, why do I need this date window? And one of the problems we've come across is some customers, they can't guarantee that they will always generate a unique key. And what happens is their systems tend to roll and they reuse keys within a time window, whether that be a day or a week or a month. So rather than searching for a unique business key for all time, effectively, we're just looking over our shoulder for a certain window to say, yeah, okay, if I detect a duplicate in that window, that's probably a resubmission, so I'll throw that one away. Okay? So let's have a look at that actually running. So here's that same process. I'm going to deploy this directly from the modeler. So to facilitate that, the actual code I'm using in here is just going to be Groovy script, which means I don't have to package it up and compile it, etc. So you can kind of see there's that query, pretty straightforward. So I submit that, deploy that to the engine. Now I'm going to go over to my REST client. You can see here I'm just using the REST API. I'm using a REST client here. I'm going to start a process instance. I'm going to give it a key. So I've got a positive 200 there, so the engine accepted it. And now if I get into processes, we'll see that that process actually ran. But if I look at the history, it went straight through. Happy days. But what if in this submission, I'd got an error? So what we want is the client, if you get an error, as in a lost response or a lost request, etc., just resubmit until you get a positive acknowledgement. So if this client resubmits with that same key, again, the client will get it back at 200. And if I now look at the history and I refresh that, we can see here that that second one, it did detect that it was a duplicate and it got routed through to there. So now we're good. And just to show that it's not a fluke, if I generate a new business key and I send that one through, and I refresh this, so good. So I've had 2 positive instances and 1 duplicate. That's all good. Oops. Bear with me for a sec. But there's a problem with that, which is what if the client wants to know which particular instance actually completed the process? You know, that prime model doesn't work because as far as the client's concerned, a process instant worked and there was only one. But what if I need to know which particular one? So with that, we can use a similar pattern, but rather than detect duplicates, we actually get the client to tell us which one it is going to be acknowledging. So it's a bit like the TCP three-way handshake. So the client initiates, and when it gets a positive response from the engine, I get back a reference number from the engine. So now as the client, I can send a message back into the engine with that reference number saying, that is the one which I want you to keep going with. And you can kind of see that in this process model. So the client starts an instance, we synchronously validate it, and if it's valid, the engine will return control back to the client with a reference ID. The client can then pass a message in with that reference and say, oh, good to go. So what happens if we get a transient failure during the initiation phase? Well, an instance will start, but the client won't get a response. So if the client resubmits, they do get a response, they then send in this message. And what we do is we wake up all the process instances relative to that business key. One of them will get a variable from the client, which is its own ID. So we can use this gate to say, that's the one the client acknowledges as performing the process, so we'll route down and complete the process. If the variable supplied by the client does not match my ID, then that's a duplicate, so I'm going to route down that other path and end. So let's have a very quick look at that. So again, we've just got this message correlation. I can deploy this into the engine. Then I'm going to start up a request. I'll give it client ID 1. I'm going to, now just imagine that that failed and I didn't get a response, so the client restarts, reattempts. So I've got 2. So if I look in the engine now, and I go to our different pattern, you can see that I've got the 2 instances there waiting. So now what happens is the client needs to inject that callback. So to do that, I need to just get the ID. So bear with me as I copy this, because this is tricky to copy. This is my ACK message, so I'm just sending in a message. I need to pass in this ID. Okay, so let's see how that goes. So you can see I've got the business key. I've got 2 processes waiting. I'm going to send in this message. I get back a 204. If I refresh the engine, no process instances. And if I go to the history, we see that one was acknowledged and went all the way through, and the other one was routed. So happy days, we're all good. But this is interesting in the API. You'll notice here, I used a flag all equals true. Strictly speaking, in BPMN terms, a receive message task correlates to a single instance. It's not like a signal. So the trick here is, how am I sending in a single message, but it's correlating to multiple instances? So that's where this flag in the API is correlate all equals true. So behind the scenes, the engine is finding all matching instances and just effectively duplicating that message and sending it to them all. It's a really convenient thing at times. But it has a catch for this particular pattern. So now as a client, I've got no receive tasks waiting. What happens if I call this API? I get back a 204. So if a client uses this, it's getting back a positive, yeah, no error, it's all good. But it didn't actually correlate to any process instances. So whilst this pattern works, have we really achieved idempotency? Now, we have achieved idempotent start, But we've now shifted the problem to idempotent message correlation. So if I wanted to deliver a single message and I set this to false, which means I really want positive acknowledgement that you got this message, when I send that into the engine now with no instances waiting, yep, it happens. But the problem with that is if I do have multiple instances waiting and I'm only correlating to a single one, then what happens to those other instances? So in that particular case, what you could do is we could just put a timer on that wait. One of them gets correlated to and the processes go through, and for the rest, effectively they just time out and passively disappear. So that's one way. But as I said, we can do it smarter, and that's about how can we introduce correlation into our messages. So here's another fallacy of distributed systems processing. Guaranteed once message delivery. It's really hard. So what do? We have guaranteed at least once message delivery. So as a client, it's like, yep, if I don't get positive acknowledgement, I'll just keep replaying this message. But in this case, we don't have the luxury of just starting another process instance. We actually need that message to correlate to a particular instance. So we just can't blindly keep on replaying it, because if the client sends the message and we get a transient network failure, how does the client know, did the server get my message? I don't know. And this message is really important to me as a sender. What if it's a confirmation of payment? I get a transient failure, so maybe my message didn't make it to the server. I get no response at all. Did the message get to the server and I lost the response? Or did the message get to the server and the server threw an error? I don't know. So again, we kind of want this idempotent message delivery. So how can we achieve that in our process models? It's actually really easy. These non-interrupting inline sub-processes are really useful for this. So let's have a look at this use case. So again, I've got an order process. Client submits the order, and it gets validated, so it gets accepted. And then the server is waiting for a receive payment message. So our client needs to send a payment confirmed message. So think about this as a state machine, and we're in two states here. There's the state before the server has received a message, and then there's the state after the server has received a message. And the behavior we want before the server has seen this message is exactly as per the process. I'm in a receive state. I'm waiting for that message. But once the server has seen that message, the behavior we want, if that message is replayed, is, well, there's really nothing to do process-wise, but I want to acknowledge that message. As a client, when I replay that message, I will get that positive acknowledgement that you really did get my message. What else can happen here? Well, we can get a race condition with the received message. So what will happen there is the client sends a message and then the client sends another message. You could get an optimal locking exception. Optimistic locking exception, sorry. So if that's true, again, if the client gets that kind of error response, it's not a hard error, so they retry. And if the first message got through, the second one will be absorbed by this inline event-driven process. The client will receive acknowledgement. So we're all good. A couple of other things to know about this pattern. You'll notice that the right-hand side is a dwell. You have to kind of determine how long you're going to wait for these duplicate kind of messages or these second ones. So if your process runs really quickly, you might want to put a dwell on just to get the process to linger for a little while, sufficiently long for the client to replay a message if that's true. But you have to be careful with this, because if you're relying on analytics for determining how long your processes take, remember that this dwell is going to make the end time look longer than it really looks, okay? So just be aware of that. But that's one way of achieving idempotent message correlation. Another problem we face is, what do you do when a system has or a service has limited resources? Now, we face this in the real world. I've had on-premise systems which are really designed and tuned for batch processing. And so the system administrators, they say to me, oh, you know, if you could kind of limit the number of requests to n per unit time, that's our sweet spot. So can you please do that for me? We have SaaS providers who impose rate limits. Now, normally they're quite large, but rate limits. They can impose rate limits per unit time. They can impose maximum concurrent requests. I've even had experience of a service, external service in production, where it was limited to 2 concurrent requests. And it's like the service provider says, whatever you do, you know, no more than 2 concurrent requests. It's like, seriously, 2 concurrent requests? But yeah, you have to deal with that. So what's the problem? Well, if you're using something like a Tomcat engine, you've got the entire thread pool or the entire job executor pool which could possibly make these calls. And that could flood or swamp or exceed rate limits, et cetera, et cetera. So how can you kind of throttle this? Well, one way we used to do it using just Java was a semaphore. So semaphore is really cool. It's kind of like, it's a gatekeeper. So we declare a semaphore with how many resources. And then you could put this code in your service tasks. And whenever a service task needs to call this really kind of restricted resource, it's grab this semaphore. Once you've grabbed the semaphore, use the resource, release the semaphore, you're good to go. But there's some problems with this, that this is a blocking call. So whilst this will address the problem of limiting how many concurrent requests you get, as far as the job executor is concerned, it's a spin lock. So you're protecting the external resource, but now you're consuming your own job executor resource and you're tying up resources in the engine, which, you know, it could be doing better things. So how can we kind of rate limit intrinsically our processes? And this is one pattern we've kind of used, which is we use the semaphore. But we break it into these 3 pieces. So step number 1 is acquire the semaphore. And if I acquire the semaphore, keep going through and use the protected resource, make the call. And when you've successfully finished that, release the semaphore. So that's a happy path. But what if the semaphore is unavailable? There's already too many clients. Well, rather than block, what we can do now is we can throw a BPMN error, which routes us through to this receive signal. So now when I've got more concurrent requests than the external service can support, those requests will queue up in the catch signal. And when the resource is released, each thread which releases the resource throws the other signal, which then effectively wakes up anybody waiting for this resource, and we go around the loop again. So let's have a look at that in action. So here's our semaphore pattern. Now, if I again look at the Groovy code for this, you can see it's pretty straightforward, which is I declare a semaphore, I try and acquire it, and if I can't acquire it, I throw this BPMN error. Now there's this really cool call, try acquire, which basically says, if I can get it, I'm good, and I'll return true, and I'll lock it, and if it's not available, I'll return false. So effectively, it's not a blocking call, but we straight away know whether we got the semaphore or not. And as a consequence, if I can't get the semaphore, throw that BPMN error, which is enabled me to go around the loop and go to sleep. For this one, for use the resource, I'm just going to sleep for 10 seconds, and release semaphore, again, is pretty straightforward. We just call the release. So I'll deploy that. Deploy. Go into my REST client. And just a really basic start here. So I start that instance. Go into my engine. Go into my semaphore pattern. And effectively, I've got that one process. And if I go to history, you can see it just went straight through because it didn't have to wait. So now let's start up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 concurrent requests. Go into the runtime, refresh. And you can start to see now that I've set the resource limit here to 2. So there's 2 processes currently in the job executor, and they're blocking for that 10 seconds using the resource. And there's 8 waiting, and if I refresh this, hopefully some of them will have finished. And yep, so we're now down to 4 and 2, etc. So that's a way of resource limiting. Service router. One of the problems we faced in our early days was we used the big monolith shared engine and we put all of our business processes in there, but that causes problems. Upgrading the engine was tough because we had lots of business units and we couldn't synchronize them, etc. So what we did is we started to unpick that and we put different process instances into different engines. But now the problem we faced was we get an order coming in which has multiple line items, and each line item is now processed by a different engine. So we needed some way to decompose the orders and route them to their respective engines. So how do we do that? So again, we have this really basic process which we accept an order, but then there's a multi-instance here which is for each line item. And for each line item, what we do, we use a DMN table to look up which version, which location, and what do I do with this particular product. The happy path is once I've got that, I now make a call into the target engine with a definition ID, and I can get the actual instance or the version I want to start. And now I can use these 2 patterns we just looked at, which is I can start a new instance, I can correlate back to that to acknowledge, yep, that's the instance I want to run. A few things in here. In the decision table, we can set the disposition to, sometimes we want to take engines offline, so we want to kind of queue up and store order or line items here, so we can set the disposition to suspend, and they'll sit there waiting for a signal to come in when the operators have brought the engine back up. If there's an error, of course, we can resolve it. This is pretty straightforward. But the trick here, or the key here, is what's inside this decision table. Whoops. So if I look inside the decision table, it's pretty straightforward. What goes in is the product ID of the actual order line item. And in here, we have an effective date. So for product A, I've loaded up that in the future, I want to use this instance, but right now I'm going to use this instance. We can put the host where that particular product will be fulfilled. And in this case, I've set the disposition to be processed. Trick with this decision table is we use first, okay? So that's why this date order is important. This is the effective order date. So the cool thing here is we can load this table up with a new kind of route or host, but it won't come into effect until midnight tonight, okay? So effectively, the system will automatically just roll over without any operator input by preloading this stuff just based on that effective date. So this is kind of like just a way of doing service routing. It really helps with operations because we can take those engines offline, bring them back up, we can deploy new versions, we can load into this table when we want to do the cutover. And the other nice thing is if we base that date on effective date, new orders can use the new version. Old orders which were delayed can still be using the old version, so we can actually interleave those versions. Okay? So decision tables are kind of good for that. Right, I keep on hitting the wrong button. And the last one I want to talk to you, fail fast, fail safe, best efforts. So what happens when you're calling a remote service and it's not a transient fail, but you don't have a transient network fail, but the service fails? So in this case, rather than just throw an error back to the client, this pattern wants to fail fast because we don't want to bring down the rest of our network or our system, but we want to fail safe, which is I want to acknowledge that request and I'm going to deal with it asynchronously. Now, Bernd talks about this quite a bit using his flight check-in example. So if I can't check in right now, rather than throw an error to the customer, it's like, why don't you acknowledge my request and deal with it? So very simple process which can follow that. We start over here with, so this use case is our customers might submit some addresses for postage labels or delivery labels. And what happens is we validate the address and we produce the labels. But sometimes the address validation service fails. It just blocks, etc. So how can we give a great client experience? So we use Synchronous here. So the client will synchronously request, and if it all goes well, they get their labels. But if we get an exception, we kind of fail over to asynchronous processing. So again, we throw a business error, which then means we go into this asynchronous, so we can acknowledge to the client, yep, I've got your request, and then we can process this in the background. One of the cool things with this pattern is we're now using the job executor here, but sometimes I still get these failures with the retry strategy. So rather than throwing an exception or an incident in the cockpit, sometimes we don't actually need address validation. 99% of the times the address is correct, so why don't we just ignore it in this case and keep going? So we can kind of get that softness. So there's a few tricks in there into how to intercept the retry strategy in the job executor. I won't go through that code now, but if anybody wants to do a deep dive into that, feel free to come and see me. Questions?
First of all, a big applause.
There you go.